Let us welcome our next keynote presenter. It's none other than Dr. Jing, who's not a stranger to us anymore when it comes to NCWE. And yeah, I think Dr. Jing is ready to give his presentation along with his colleague from Delft University of Technology, Dr. Wang. I believe he will take over from Dr. Jing after the first 30 minutes. And I would like to call upon Associate Professor Dr. Guoqing Jing from Beijing Jiaotong University, China, with his topic on smart and sustainable railway sleepers. Take away, Doctor.
Okay, thank you. And it's nice to share some of my research with you. And it is very new and share with my friends. And I like to contribute and develop some kind of research like sustainable and smart railway sleepers. And today my content, like the first one, can you hear me? No problem, I think.
Yeah, we can hear you, Doctor.
Okay, this is the content. First part, I will make a short, brief introduction about traditional railway sleepers. And secondly, I will make some introduction for sustainable and recyclable railway sleepers, which I have been working in the last 2 or 3 years. And the next part is some of my perspective.
Could you turn to the slideshow mode so we can able to see?
Okay, which means.
Sorry.
Okay, I got it. Okay, like here. Okay.
Okay, good.
Okay, that's much better. Okay. This is my content. First part is traditional railway sleepers, like, for example, timber sleepers. And the advantage is very easily available to everywhere, from America to Russia. But the problem is short life. Normally, the maximum service life is 20 years. And after the World War II, we use pre-stressed concrete railway sleepers. And this is the main type of the world. For example, in China, more than 95% of railway sleeper is made of real concrete. But the problem is not environmental friendly and too much stiffness, too rigid. And the one part is between the World War I and World War II. Some countries, even in, for example, in Brazil, in Australia, for some heavy haul railways, they use steel sleepers. But the problem, because of the surface of the steel and the light weight, there is less interlockability for the track stability. And this is timber sleepers for the production, the short life, durability, and sometimes very sensitive to the temperature, to weather, and mostly for the water issues. So we have to use chemical anti-corruption things, materials, crystal. This is in European way, it is forbidden to be used because of we think this is very bad to the health. And for some concrete sleepers, they have lots of the advantage: strong enough, easy fabrication, and good quality. But the thing is too heavy. Each railway sleeper, it weighs up to more than 300 kilograms. For some railway sleepers in China, more than 400 kilograms, too heavy to manipulate. And lower resilience, high stiffness. High stiffness results in more dynamic force and difficult to transport because it is structure of pre-stressed. And most importantly, it's high energy consumption, totally made of cement, steel bars. And the next one is the traditional railway steel sleepers. High cost because made of steel, and less resistance, which means interlockability because very smooth surface, and corrosion issues, and poor vibration because less in mass. So there are lots of problems recently, like environmental protection and sustainable development in China, for example, because of environmental protection, the price and availability of gravel, sand, aggregates becomes very difficult. So the companies try to use recycled materials, for example, like glass and furnace slag, and even sea sand. We wash the sea sand once again, once, and also man-made sand. This is because of environmental protection. Lots of the aggregates factories are closed. Another thing is special, extreme environment. For example, Tibet Railway, cold, freeze, and thaw. It's not only in winter. Every day it's like goes through a cycle of freeze and thaw. This totally deteriorate the concrete material. Another thing, new track structures. New track structures, for example, rack railway, this is rack railway for the tourism in well developed in America and Europe. But recently in China, lots of the cities to investment and develop this rack railway structure for tourism, for mountains. So this is different structure. And the middle span, this has a force connection with the track. So so in view of this kind of challenges, problems, my team and I developed a railway sleeper research. We developed new steel sleeper and composite railway sleepers. We collaborate with industry for the material selection, designing, fabrication, and testing. And for example, this year I have one student working on rubberized concrete sleeper. And I have Mongolia PhD students working on UHPC sleeper, which ultra high performance concrete sleeper. Very strong, it's like kind of steel. And I have students come from Africa, and they're working on bamboo mixture of recycled plastic and bamboo fibers with reinforced concrete sleepers. This is my undergoing research topics to produce more green and sustainable railway sleepers, as well as resilient railway sleeper. Now we talk about the steel sleepers. They have lots of advantages, like 100% of recycled and widely used for heavy haul, for cold regions, and have very lower structural height and mass, and long life service. This is the transportation, production, but they have problems. So my work is collaborating industry to produce and to apply this patent. This is use the rubber mat under the bottom to provide elasticity, to reduce noise, to increase damping, and to extend the service of the ballast bed. Another thing, this is one of our patent to increase the interlockability, because the railway sleeper, the lateral force easy for losing stability. We use this web, one web, two web. We publish papers in CBM, in construction and building materials about the steel sleepers. There are lots of the things. We also made some material science working with the company to add some like copper, like a titanium, to made new materials into the steel sleeper to extend the service life. And we're also working with this is some other this is Pandora from UK for developing the real fastener. This real fastener is good for the isolation for the track circuit. And we want to this is our type developed, use plastic used in Africa for some company. And the next part is composite sleeper. What is composite sleeper? Composite sleeper, in fact, developed into two types. One type is used like chemical polyurethane foam, like FFU sleepers. This type. This is totally new, very expensive. Each sleeper is like 700 US dollars, very expensive. But this type use recycled materials. Another type use recycled materials, very cheap, like 100 US dollars. Recycled like rubber, recycled plastic. They have behave like timber, but reduce the timber use. It could be renewable and recyclable, high and good environmental adaptability. This is all the new types developed in China. This is a recycled plastic from rubbish. And this is plastic UV sleepers. And this is FFU, fiber reinforced polyurethane, FFU sleepers. This is very expensive, very strong, but it's not environmental friendly. This is environmental friendly, but the problem is lower ability. We are working on several solutions. For example, this is how to produce the composite sleepers. I can share the PPT with you after the lecture. And this is our research. This is some other country. This is from Netherlands. We are working with Technical University of Delft for the simulation with steel bars reinforcement and with fibers, with all kinds of fibers. For example, glass fibers, to increase stability. Another thing is we use material science. We can also use FEM simulations to optimize structure and to increase the resistance. What is the resistance? Interlockability with the track. And this is our patent. This is some kind of our patent for our simulations. Steel structures for steel bars. And this is our patent of composite UV sleepers. So I'd like to develop international cooperation for composite UV sleepers. Use local recycled materials like even coconut, even like the shell of the fruit. All kinds of fibers, like organic fibers. Another thing is this is one of our research. We use the standard, use the DIC method for rubberized concrete. What is rubberized concrete? They have lots of the good ability. For example, we can reduce the stiffness. And of course, with the rubberized particles into the concrete, it will result in the strength decrease, but it is also within the acceptable group standard. They have very good ability for damping, and impact loading resistance, accent for frost resistance. This is our research. I have one master student thesis working on rubberized concrete sleeper. And this is part of his work from the production, concrete making, and the comprehensive and all the traditional concrete test. All the test of this is for bond strength test, and for production of the UV sleepers. We produce the UV sleeper and we made some basic test the test result shows that with good ability of damping, like 10 to 20% of increase, and good ability for frost, freeze, and thaw ability. Another one is UHPC sleepers. UHPC, this is it's like kind of steel. It's like kind of steel. We can use less steel bars, and we especially good for very cold regions. For example, in Mongolia, the minus degree is minus 50 degrees in winter. Also could be used for our Tibet railway because it needs less of maintenance and inspection. This UHPC sleeper. Some papers published in construction and building materials about the UHPC sleeper. If you can Google and use this keyword for working. Another thing is bamboo. This is my work undergoing now. We use bamboo sleepers. Two types. This is one type. Use most of the bamboo and bonded with glooming. This is bamboo, temperature, drying, fibers, and this compression, glooming. This produce this type of UV sleeper. This is bamboo with bonding materials. We call it bamboo polywood sleeper. Another type is we use bamboo fibers into the composite recycled plastic UV sleeper. Use bamboo fiber to increase the stability of the UV sleeper. I have a student who come from Guinea working on that. And we also have one idea is working on use bamboo fibers into concrete UV sleeper to increase not the load ability, but the ability to extend the cracking ability. Next one is resilient sleepers. This is one of our working. We use under sleep pad, which is made of a composite or polyurethane or rubber under the sleep pad to increase the contact area. Normally, the traditional ballast track with concrete sleeper is just 3 to 5% of interaction. Less contaction area, a higher stress, more damage. So there are lots of other researchers and they use rubber or the pad or the other type of the material to produce the pad to increase the track structure service ability. For example, like one time of increase for the ballast service time. The ballast under sleeper pad has a life service time more than 40 years and very easy for installation and no damage for transportation. Very good for use. Provide more elasticity and interlockability. But pay attention to the dynamic, like the soft stiffness selection in view of different railway conditions like heavy haul, mainline, and urban transit. For example, this is our product. We're working with company for the material science with chemical background and civil engineering for installation UV sleepers. And we did the test. This is our partial coverage reduced because it's part of less contact with the sleeper, with the ballast and less dynamic force. All dynamic force focus on under the rail head. This is part of my work, and I use less time than I expected. So anyone, do you have any questions regarding my sustainable UV sleepers? Hello? Anyone who has questions regarding, can share my.
Yeah, if there are any questions from the participants, you may ask.
Yes,
Yeah. So there is one question here from Mr. Beng Wei Chong. And the question goes, hello, Prof. I'm Beng Wei, master student of UMP. I want to know more about UHPC compared to pre-stress sleeper. How do them compare when it comes to strength and durability?
Okay, that's a very good question, and this is our UHPC sleeper. Okay, look at here. UHPC sleeper, it's called ultra high performance concrete. The strength can up to 150 megapascal. It is 3 times in the common railway concrete sleepers. It needs less pre-stressing tendons, and which means less of there's almost no pre-stressing tendons, which is easy for transportation. And this UHPC is made of steel fibers. Steel fibers, 5% of steel fibers in mass, very strong. It's like so with very strong ability, so we can reduce the size. For example, we can reduce the, I have photos, I can share some photos with you. The UHPC sleeper can use almost 2/3 of the traditional railway sleeper size. Easy for transportation, especially for long distance. Secondly, in view of the UHPC sleeper, it is totally free. It's some kind of totally free for freeze and thaw. Normally, for the common railway sleeper, the freeze and thaw test 300. With 300 times test, the common railway sleepers almost some kind of damage, lots of damage, like 20% to 30% damage. But for our UHPC sleeper, after 300 cycles of freeze and thaw test, just 2 or 3% of damage. So it's very suitable for extremely cold regions. And we can prolong the service time. For example, normally the railway sleeper is 50 years. We can prolong like 60 years. So less for maintenance. Another thing is very good for fastener installation. UHPC sleeper, there are 2 papers like from Korea, especially Korea, very cold regions. This is one of my PhD students from Mongolia, because they are exposed to very cold regions, and railway is heavy haul to transport the coal and very huge dynamic and fixed loading, and the lack of the inspection work. They prefer to more reliable and safety railway structures. UHPC is not only used for railway sleeper, but also could be used for railway other structures. For example, like for the bridge deck board. This is my. If you are interested in this, you can find with UHPC sleeper, and I can share his like mid report about his thesis, and this is some of my question. I hope you can I hope I can answer your question. Okay, thank you.
Doctor, there is another question here from Mr. Do. The question is, the product is very impressive though. So how about the cost of sleeper compared to their existing sleepers when it comes to
UHPC sleeper, or I can reduce. Okay, I can reduce from here. Okay, this is very interesting question. I can show here. Very interesting here. Steel sleeper in China is like 600 like RMB, which is almost 100 US dollar. Here, 100 US dollar. The common traditional railway sleeper, concrete railway sleeper, in China the price is like 30 US dollars. This is in China the price. But when it comes to, for example, USA, the price is totally different. In USA, the concrete railway sleeper is 100 US dollar. The timber sleeper in USA is 30 US dollar. But in China, the concrete railway sleeper is 30 US dollar, but the timber sleeper is 100 because of America is rich in forest. So that's why America, US railway, 80%, 85% of railway sleeper is made of timber. This is about railway concrete and timber sleeper and steel sleeper. Composite railway sleeper, this is varied a lot. Some composite railway sleeper with just 30 or 40 euros. But some very good quality, even made of recycled materials. For example, a Germany company, the recycled plastic composite sleeper can sell at 250 euros. It depends on the performance and the size. Some other like UHPC, like FFU railway sleeper, is like 700 US dollars. Very expensive because it's made of new chemical materials, very expensive materials. Rubberized concrete railway sleeper, it is almost the same price as common concrete railway sleepers, and with very good ability in like freeze and thaw, damping, and stiffness reduction. This is our new this is we rank it very top, and we are working with company to make it more used in not only in China. We are working with Australia to make it as a good product for heavy haul railway. UHPC sleepers, the problem is for this too expensive. The price for each sleeper is 150 US dollars, too expensive compared to the common railway sleepers. So it just could be used for some special occasions. It could not be a very good solution regarding the price. Bamboo sleeper, bamboo fibers, in fact, very strong. Some ETH from Switzerland call it like has a very strong tensile strength, like 100 MPa, very strong. We use the fibers to produce railway sleeper. I think it with good ability for resilience, but less in increase bearing ability. We are working on bamboo sleepers. We are still not have too much results. Resilient railway sleeper, the US we call under sleeper pad. In fact, is made for high performance composite materials. Depend on the size. Our product, our company product, we collaborate with the company. The price too high, like 100 US dollars for each sleeper. So because of the too expensive, so the marketing not good. This is in China case, but all the new railway lines in Australia, they should be installed with under sleep pad, depend on the country conditions. I'm working with UMP, and I would like to produce working on like sustainable railway sleepers, like use local materials to reduce the waste and to produce more eco and environmental friendly railway sleepers. Okay, I hope you are.
Yeah, thank you for that answer. And can we have Dr. Noram with his question, please?
Okay, thank you, Mr. Dr. Yoben. Hi, Prof. Jing. How are you? Okay, just a very short question. I'm kindly interested in when you speak about bamboo. We noticed it was about 69 billion USD bamboo markets, and China is controlling 39 billion USD per year. Is it in China? I think that is it in China they already have the manual or standard which refer to bamboo as an application in a structure. Is it you have that in China?
In China, up to now we don't have the bamboo-based railway sleeper, but we made several railway sleeper that made for bamboo. It is stronger than the timber sleeper ability. We have the timber standard. We have the timber railway sleeper standard. So the ability like the bearing, the seat loading, and how, because bamboo is more strong than the timber. So this is some totally like bamboo.
The standard is inclusive in the timber standard.
Yes. It in accordance with the timber sleepers.
In Chinese character or English?
Chinese.
Oh.
In fact, we can show that the bamboo sleeper is good for the to use in other country for the railway sleeper to compare with the timber sleeper. Timber sleeper, in fact, the ability lower than the bamboo sleeper. The problem in China, the bamboo sleeper is also very expensive. This sleeper is like 1,000 RMB, which is 150 US dollars. It's like 5 times of the railway concrete sleeper and 2 times than the normal timber sleeper. We are working on to use more solutions to reduce the cost.
I think that answers Dr. Noram's question. Thank you. And we have 2 more questions for you, Dr. Jing. I hope you'll be patient to answer. Now, Ben asked you another question. How can these sleepers resist 4 seasons environment and also the extreme temperature changes in China? Do you think all these sleepers that you are researching capable of resisting these extreme changes of weather, like in China or in any other part of the world?
No, not all sleepers can reach the standard or can make to face the challenge of the environment. But some of the railway sleepers, for example, like rubberized and we call it modern composite railway sleepers. The common, I can show you this one. This is a very interesting one. Is like here. This one. The common composite sleepers with the companies of railway, they use just the recycled materials without fibers, without steel bars. So our solution is to use fibers, all kinds of fibers, metallic like steel fibers, glass fibers, and even organic fibers like bamboo fibers to reinforce the loading ability. One thing more is not only the ability for the load, but also the ability to against the temperature variation. Because this material is totally made of the plastic or rubber, with temperature increase, there will be because the material has a higher coefficient of temperature. With normally for this traditional railway, composite railway sleeper, with temperature variation more than 40 degrees, there will be too much deformation. They could not keep the right position of the track, resulting in track geometry problem. So my team, my students working on use steel bars for simulation to define the location, the size, the number of the fibers, not the steel bars. This is KRP, Netherlands company use steel bars. And our solution is not use steel bars, use fiber, glass fiber, has more ability of less coefficient of temperature, can constrain, hold the composite sleeper deformation with equivalent to the temperature. This is our working to increase the ability. Another thing is to make component approximation with fibers and some like aggregates, some more easily bonding aggregates to create new sleepers. This is our solution. Okay, next question, if I can.
It looks like we are running out of time, and I think we should give way to the second presenter. And I would like to thank Dr. Jing once again for your informative presentation. And with that, let's welcome Dr. Ho Yu Wang from the Delft University of Technology with his title, Structural Health Monitoring for Railway Track Transition Zone. Please, Dr. Wang, you may take away.
Hi, good afternoon, everybody. My name is Hao Yu. Can you see or hear me?
Yeah, Dr. Wang, yeah.
Yes, doctor.
Yeah.
Yes.
Crystal clear.
Thanks a lot. Thanks a lot. First of all, it's a great honor for me to present here. Thanks for the invitation of the conference committee. My name is Hao Yu, like how are you without the R? So nice to meet you, my dear colleagues. As you may know, that Professor Jing has a lot of international cooperation. And then today I would like to share one of the results of Dr. Jing's cooperation with TU Delft, as well as Fugro, that is a company in the Netherlands. And the title of my presentation is Structural Health Monitoring for Railway Track Transition Zones. So in this presentation, I would like to share some very new technology that has been used for railway infrastructure, and hopefully it can bring you some new ideas, could use some technology for other infrastructure inspection and monitoring. And during my presentation, feel free just to raise hands, then I can just, if it's short, and then I can give directly answer. If that is allowed by the conference committee. Okay, so a little bit introduction of myself. I did my bachelor and master degree in railway engineering in Beijing Jiaotong University. During that time, I was supervised by Professor Jing. And then after that, I went to Delft University of Technology, the railway group for PhD. And after I finished the job of my PhD, I work as a railway consultant in a company in Finland The name is Rail Scanners. Now it's acquired by the company Lorem. And after that, I come back to the Netherlands. I work for the company called Fugro as a railway specialist, as well as a project leader. And after that, well, at the same time, I also work as a postdoc researcher in the railway group of TU Delft. And in this year, I joined the SAN committee and the ISO committee as railway expert. So trying to make some standard or norms for the railways. So maybe you are not very familiar with railway transition zones. What is a transition zone? That is the location that's where the different track has just connected. So a very short explanation is when we have a bridge on the railway, there is always a connection between the bridge and a soil, let's say embankment at two ends of the bridge. So when we first constructed the railway, it is a very smooth and straight line. But after a few months or years, the tracks start to degrade. And this is very often observed that we can see very large local settlements at the end of the bridge. We have an example to show you. So this is a very small bridge. Here you can see, and there is a very small river go under it. Here we can see that the rail, we have ballast sleeper here. So we have ballast track and wooden sleeper. And then we can see the rail go across the bridge here. If we look from a different angle, we can see that the railway, it's deformed. So this place looks it go up a little bit, and the railway before and after it goes down. So that is deformation, and something like this. The only thing is that the bridge here is actually not. It does not go up, but it's the embankment goes down. So it looks like the bridge goes up. There are some other transition zones that we can see from other tracks. So whenever there is a connection between a bridge and embankment or a tunnel, there will be a transition zone, and there will be problems. So as you may know, that the railway track has been inspected once per. In different countries, it differs. In the Europe, the railway track has been examined once per 6 months, so that's twice per year, using a track inspection vehicle. And when we run the vehicle along the track, we can measure, let's say, how smooth the track is. It's something like this, and there's a terminology for it. It's called longitudinal level. But in theory, it should be a straight line, as you can imagine that when the railway is just very new. So it was a straight line, but then after several years of operation, they start to have a lot of up and downs. And that is actually what we see in the previous figure. So there are two pits before and after the bridge. And let's say if we track those two bottoms, what we can see is another measurement in 12 years. So we can see that this is the vertical displacement of those two bottom points. What we can see is that the bottom point was -6 in the year of 2005, and then it started to grow bigger in the year of 2006, it was restored. So it was lifted a little bit by tamping, I guess. And then start from the year 2006, it started to degrade again. So until the year of 2010, it was restored again and degraded afterwards. So that is the situation, that the track transition zone has been always degraded, and if you do not do anything, it just grows really bad and grows fast. So that's why we need to monitor it. When we have those large deformation, what we can get is the bolus and slipper damage. So this is an example to show that the slipper are crashed in the transition zone. Sorry. And also we can expect the passenger comfort will be deteriorated. According to the research in the Netherlands, the maintenance cost in the transition zone is up to 8 times compared to the normal track. So that is, let's say the railway bureaus, railway owners, they have to spend a lot of money to maintain the quality in the transition zone. And the current inspection method, as I explained previously, is only using a large track inspection vehicle. In the Netherlands, it's called UFM 120. In China, it's called Yellow Doctor. It just differs every country, but it's very expensive no matter in which country. So that's why normally we can't perform the measurement like very frequent, because it's very expensive and it has a track possession. That means the track has to run on the train has to run on the track, and it costs fuels and powers and so on. We think the object of can be examined by this vehicle that is track geometry, that is too less. We want to examine more things, and also we think using this vehicle is too expensive, and also the frequency twice per year, that is too low. And then we, in this presentation that I'm going to show you, some measurement methods that can examine more objects and with less expensive price and with high frequency. I'm going to show you 3 innovative inspection methods that has been used in the Europe. So the first one is just using InStar. It's a satellite-based technology that we can see the track settlements. The second one is called the DIC-based method, that is using a camera-based measurement system that we can put the camera outside of the track, and then we use the camera to monitor the track deformation and the track deflection during the train passing. The third one is a new system called Ryla, that is a mobile system that can just install on the end of the train, any train, passenger trains. So we can install the system to a passenger train to measure the track geometry. Then we do not have to use the large vehicle, but only a small box. And the third one is called ground penetrating radar, GPR for short. It can measure the bolus condition. So those 4 is we are going to discuss. The first one, DIC. So it's short for the digital image correlation. So that is actually a very simple technique if you think about it. We have a high-speed camera and we put outside of the track, and then we put some kind of target on the rail or sleeper. And then during the train passing, we measure the vertical displacement of those targets. So that's how we do it. We have to enter the track, and then we drill a wooden sleeper, so that's easy for us. So we drill holes to the wooden sleeper. In case of concrete sleeper, then we can glue them. And this, for example, when we want to put the target on the rail, we can just glue them. That's quite easy. So this is the measurement location that we did. It's in the Netherlands. Another transition zone. Here you see the river clearly. So this is a photo that we took besides the railway. So here we see that the track on embankment, and this is the track on a concrete bridge. That is a photo taken after we install all the targets. So here we see that this is the track on the embankment, and this is the track on the slab track, on the slab bridge. And this is a wider photo that we put the targets on several sleeper next to the bridge. And then we put our camera here. We set up our laptop here, and then during the train coming, we measure the vertical deflection. This is another photo show that's our camera. And this is the laptop view. So I can show. So after the train, yeah, you see, if we focus on this target, we can already see that this is the vertical deflection of the rail. Okay. Next slide. And then we can see some, let's say these are the vertical displacement of the rail that next to the bridge and far from the bridge. So I count rail 1 from the bridge, and then this is the vertical displacement of rail 3 and rail 9. So there we see the rail 3, so the sleeper close to the bridge has much bigger vertical displacement than the rail far from the bridge. And a summary of the measurement that we did. So this is the bridge. It has been shortened. We can see the maximum of the vertical displacement of rail that's close to the bridge is much bigger. So that ups to 3 millimeter. On the other hand, the sleeper or rail that's far from the bridge has only 1.5. So they are like 2 times compared to like close and far. So we have proposed this track transition quality index, which is the average displacement of a transition of the rail close to the bridge, divided by the rail or sleepers far from the bridge. So that is a very simple calculation. And then when the ratio is too big, let's say in this case, is 5, that means the rail close to the bridge is 5 times larger than the normal rail, let's say. It is very poor. On the other hand, if the ratio is only 2 times, then we think is okay. So that is the first methods. And I think for the rest, I have to go a little bit faster. So let's see the INSAR. Oh, no, sorry. The first one, the next one is ground penetrating radar. So that is a radial technology that we send a radial signal to the ballast, and then we measure the reflection time and the reflection signal, the strength needs of the signal, and then we can know the depth, how much is each layer of the material on the slipper, and also the quality of each layer. And what we did for this research is we want to see how much is the moisture content. That means, is the ballast wet or not? Is there too much water underneath the slipper in the ballast? So if there is water, then it show a color of blue. Otherwise, if it's very dry, then that is in this case full of pink and purple. Otherwise, there are some points of blue. We have used this GPR measurement on a lot of track. This is a very good track, so it has nothing here. And this is our measurement. It is very dry, no blue point. And then also we measure the track geometry, as previously showed you. So it is a quite straight line, so not very big amplification. In case of a transition zone, so again we see a bridge, and then we see, after the measurement, we see there are quite many blue points. Let's say this point and this point. And those two large ones are the approach slab. So those are concrete slab just put before and after the bridge. So that is not water. So only those 4 points are water. So we found there are water actually in the transition zone. That is actually because the poor drainage in the transition zone. And we've measured the track geometry in the transition zone, and different from previous good track, we found they are quite large valleys before and after the bridge. So that gave us one explanation why the track in transition zone always poor. That is because it has the problem of drainage. So the water cannot go away from the track, and then it differs the elasticity of the track, also the temper of the track. So that is some problem of material property. So another two cases of transition zone. So in this one, we also see some water. In this one, we see even more water. That is the technology of using the GPR. And we also try to use the INSAR. So that is the full name of the INSAR. In simple, it uses satellite radar to measure the same area. And then we, the advantage is because the satellites go around the Earth once per 11 days. So we have a data point measured once per 11 days. And after we compare all the measurements, we can calculate the settlement piece of that point. And then we try to use this technology on railways. We try this technology in this long bridge. That is another bridge in the Netherlands. So that is the top view of the bridge. And this figure is the result of the satellites. We can see, we measure from the year 2009 till the year 2015. We see at the beginning that they are all green. That means there is no settlement in the beginning. And then when the color become green to red, that means this location has a large settlement. So here we see the bridge is not settled, it's always green. But on the contrary, the embankment has been settled quite a lot, especially this point. It turns red, and this point even turn black. So that means we compare this measurement results with the track geometry we measured. So that corresponds quite well. So that means the location that has large valleys, we also observe the large vertical settlement with the INSAR technology. The last one, track geometry measured by RELA. So this is a new system. It's called RELA. That is a measurement system invented by the company Fugro. So that is the company that I'm working for. It has quite many sensors, and the most important two we are using for the track geometry measurement is the IMU. So that is the inertial measurement unit, and with 2 rail scanners. So I'll first show you how we use the system. It can be easily mounted on a passenger train. So this is a passenger train used in the Netherlands. So first we put an adapter to the train coupler. And then we put the rail system on the train coupler. And the system is quite light. It's 80 kilograms, so that is it's like a adult weight. So that's it. We straighten the antenna, and then we turn the key on. So that's it. It's quite quick. Normally I take 2 minutes, but this time I take only 1 minute. What we can measure is this is the rail scanner. So it projects a laser line on the railway, and then there is a camera system that take picture of this blue line, so this laser line, with 300 hertz per second. So that means we have a 3D profile of the rail, actually 2 rail bars along the track. This is the cross section that we measured from the previous system. So all the black lines, black dots are the measurement. So that is the actual rail profile, and the green one is the is the nominal profile, and then we can compare the vertical and lateral wear from the nominal profile. So we can have like the 3D profile of the rail. A very brief look of the results that we can measure. So using that technology, we can measure quite often because it does not need the track inspection vehicle. It just needs a box. Then we can put it during the train stop. That's why we can measure the track geometry every month. And this is a measurement that has been performed since August 2018. And then we've measured the track every month. So in this peak, if we look in detail, we see that there are very little degradation between each runs. We color-coded, we calculate the standard deviation from all the measurement, that is from August 2018, and then till November 2019. So when the rail is good, it shows a color of blue, and when it's bad, it shows a color of red. So in this case, you can see that the rail, like if we see the results in 1 month, we know which location has poor track, and if we trace the railway track at the location, we can know that how it degrades. I will finish in 1 minute, I guess. So here we can see that this is a maintenance, and then we directly see that the color turn from orange to green, and then it starts to degrade again. So after this maintenance, and turn red in the year of November. And by comparison, we can see that this is with every month measurement, and this is with conventional measurements. Yeah, for the conventional measurements, we couldn't see too much information, but on the other hand, with frequent measurements, we see a lot of more information. A case study of transition zones, I think, is a similar thing. We measure it every month, and then we see really detailed degradation of the abrasion. So that is similar with the previous figure that I showed you. So I will skip it. And this is figures show that how maintenance has been done. So in the month November, it was the black line, and after in the month of December, it has been restored. So the track has been restored to the red line. Okay, so that's a summary. That's we go through 4 new methods for inspection of railway track transition zones. Thanks a lot.
Okay, cool. Thank you to Dr. Yu Wang. I hope that I mentioned your name correctly this time. And anyway, that's all the time we have, but I just want to make a quick, maybe a question, a direct question to you. First of all, that was brilliant to have so many options of techniques to monitor these tracks and the health of these tracks. But I just wonder if the results that you just portrayed here is due to the ballast deterioration, or it's because of the subgrade weakness. Because I do believe that Netherlands has a very sensitive, soft and mushy. Yeah. It's full of wetlands. So when you have this monitoring system, and then you said you managed to get the deterioration, results from this ballast. So can you explain how did you really control that?
Well, it's a very good question. I think you're very familiar with the Netherlands. We can't control it, to be frank. So that's why we want to measure it. Let's say using the INSAR technique, the satellites, we try to see how the foundation settles. And using the GPR, we see how the ballast settles. So we cannot really control it. We try to measure it as often as possible. And
so are you trying to say that those settlement it could be merely due to the soil and not really to the weakness of the ballast? That could be one of the factors. Both, yes.
I would say it's both, yes. And compared to the ballast, I would say sometimes the soft soil plays a more important role, especially in the Netherlands. Maybe not in China, but
yeah, correct.
Really soft place.
Well, I think that's all time we have, and that was a great presentation indeed. And I wish we have more time to discuss and get more info out. So finally, I just want to thank all the keynote speakers, starting with Dr. Ivana Ramli, Dr. Jing, and of course, Dr. Yu Wang, and for your great presentation.